Greetings, AP Chemistry students. This is Mr. Harper, and this is the first lecture out of Chapter 9, which is all about bonding and structure. On the next test, it's going to encompass both Chapter 9 and Chapter 10, which both have to do with chemical bonds. And so today what we're going to talk about is what chemical bonds are. We're going to talk about 3 different classes of chemical bonds, and we're going to talk about something called Lewis structures and how to draw one and what they show us for a molecule. So here we go. Let's start with talking about what chemical bonds are. Okay, now keep in mind, you can't see a chemical bond. A chemical bond is not a stick that is joining two spheres together representing atoms. Okay, a chemical bond is not necessarily a physical object you can isolate and look at under a microscope. What a chemical bond is, or what chemical bonds are the sum of forces that hold molecules together, or rather say molecules, or if we're talking about ionic compounds, formula units, little pieces of an ionic compound, like a single unit of sodium chloride, for example, or metals. Everything is held together basically by chemical bonds, and it's the force of attraction that holds those units together. Okay, we're going to talk about 3 different kinds of chemical bonds today. The first one we're going to look at are going to be ionic bonds. Secondly, we're going to look at metallic bonds. This is a little bit out of order on your note skeleton, but that's okay. And last, we're going to talk about covalent bonds and what they are and what differentiates the 3 different classes. Okay. Now, the question is, where do these come from? Okay, where do chemical bonds come from? What is it? What is the force that holds a molecule or a formula unit or a piece of metal together? And all chemical bonds have. Oh no, yes, I do not want to. Come on, Java updater, man, I don't want you to update right now. Okay. The thing all chemical bonds have in common is that they all arise from something called electrostatic attraction. This is the attraction between positively and negatively charged bodies. And, the question is, well, why do positive and negative things attract? Well, we don't really know actually why that is. They just do. It's one of the great mysteries of science. But in some way or another, all 3 of these different kinds of bonds rely on the attraction between positive and negative things. And we're going to look at in each case how that arises. So firstly, let's talk about ionic bonds, okay? Ionic bonds arise from the transfer of electrons from one thing to another, okay? Let's take a look at this picture down here. What this picture here represents is a crystal of the ionic compound lithium chloride that has the formula LiCl, okay? And what you're actually seeing here in this picture is something called a crystal lattice. We talked a little bit about lattices before. Each of these yellow spheres here represents a lithium ion. So we have a lithium ion and a lithium ion and a lithium ion, etc. Okay. Each of these green spheres represent a chloride ion, Cl minus. Here's another chloride, Cl minus. Here's another chloride, Cl minus, and what have you. Okay. Now, what the lattice is, guys, is this kind of repeating pattern of positive ion, negative ion, positive ion, negative ion, positive ion, negative ion. That repeating pattern where those ions squish together. And what holds this crystal together is the attraction between the different ions. So I'm going to use a different color here to kind of show the attraction. Let's go to get green, okay? So if we think about this lithium ion here, guys, this lithium ion is positive. It is attracted to this negative chloride ion right there. However, it is also attracted to this chloride ion here and to this chloride ion right here, okay? So we have this positive ion is attracted to all its negative neighbors. Well, in the same way, the chloride ion right here is attracted to that lithium ion and that lithium ion down here, and that lithium ion over here. Okay, so this mutual attraction between these positive ions and all the surrounding negative ions, and all the negative ions and all the surrounding positive ions. Okay, that is right there the ionic bond. Is these oppositely charged ions are all attracted to each other and they're packed close together, and so that makes the crystal really strong. The attraction overall really strong. Okay, now where this comes from, okay, is if we think about a solitary lithium atom and a solitary chlorine atom right here. Lithium has got 1 valence electron. Chlorine has got 7 valence electrons. Something we know about metal atoms, guys, is that they are easily oxidized. It easily gives up this electron right here. Something we know about the halogens, like chlorine, is that they have high electron affinities. This wants, okay, if we think about, what it wants to have 1 more electron. It's energetically favorable for it to gain an electron. So what happens when these guys meet up is that an electron is transferred from the lithium here to the chlorine, and then what we have afterwards, we have the lithium minus its electrons, the lithium plus ion. The chlorine atom, after gaining that extra electron, becomes a chloride ion, and this is Cl minus, so there we go. These guys attract each other, and that's how we get an ionic compound and how we get an ionic bond. It results from the transfer of electrons between these 2 things, okay? The next kind of bond we're going to talk about are metallic bonds. And if you want to think about metallic bonds using a little catchphrase, you can think of metallic bonds as being a sea of electrons, the attraction to a sea of electrons. This is actually, I think, number 3 on your node skeleton, but, that's okay. We can work out of order. Okay, so how metals actually exist. Let's consider a simple metal like sodium, okay? Sodium, we know, guys, has got 1 valence electron, okay? And if we were to zoom in with our magical chemistry goggles on a piece of sodium metal and examine what it actually looks like, okay, the atoms actually kind of sort of exist. You can think about like they're positive ions, okay? So these valence electrons are very loosely held and are actually shared across the entire piece of metal. And so what that really leaves is you really have like a bunch of, you can think, sodium ions, the positive nuclei without their valence electron, and these are surrounded by a sea of electrons, okay? So the valence electrons are shared between all the different nuclei here in the piece of sodium metal, okay? So here's what the the metallic bond, rather, really is. This metal nucleus right here, my sodium nucleus, which is positively charged, okay, it's really kind of like a sodium ion, is attracted to this electron right here, which you can think about is its electron, okay? This metal atom here is also attracted to this electron right here, but it's also attracted to this electron, or rather, the electron is also attracted to this metal atom right here, and also to this one right here. So you can see that this electron here is really shared, and it's really attracted to all these surrounding metal nuclei. Okay, and if you think about it, the same thing happens with this electron here. This electron is attracted to that nucleus, and to that nucleus, and to that nucleus right there. And this metal nucleus here is attracted to that electron, and that electron there, but it's also attracted to this electron here, and to this electron here, and to this electron down here. Okay, and this metal nucleus right here is attracted to that electron, and attracted to that electron right there, and attracted to that electron right there, and so on and so forth. So really what you have is you have these electrons here that are shared, that are attracted to all these different positive nuclei, and you have all these different positive nuclei that are mutually attracted to this sea of electrons here. The electrons in the metal are loosely held, they're free to move all over the place, and that's what allows metals to conduct electricity, is because these electrons don't have a fixed position, they can move that way or that way or that way or whatever, okay? Also, metals have very high melting points for the most part, and the reason for that, guys, is because this attraction is very strong. You can imagine that the more electrons that get shared here between the metal nuclei, the stronger the attraction between the metal nuclei and the electrons becomes. So, strong attraction between the metal nuclei and the electrons means high melting points, and there you go. That's why metals have the properties that they do, okay? Now, this is important. We're going to talk more about this later on in Chapter 13. We'll come back to this idea of metallic bonding. But really the focus of Chapter 9 and 10 is the third type of bonding, which is covalent bonding. Covalent bonds come from the sharing of electrons between two different atoms, okay? And to explain how this works, we're going to consider this picture down here. This is copied onto your node skeleton. You may just want to kind of write down a few things on it, okay? And we're going to consider the formation of the molecule H2, which is diatomic hydrogen, okay? Consider these two hydrogen atoms over here, okay? If we look at it, guys, we know each of these guys has got, we're going to call this, by the way, I'll call this one here on the left hydrogen A. I'm going to call this one over here hydrogen B, okay? When these guys are far away from each other, they don't influence each other at all, okay? And on this graph, by the way, the x-axis is internuclear distance, the distance between the two hydrogen nuclei. And here on the y-axis, you have potential energy in kilojoules per mole. Notice that when these atoms here are far apart, the potential energy is approaching 0. And the reason for that is because those atoms do not influence each other at all. They're not attracted to each other. They don't repel each other. They just don't influence each other at all. However, when we decrease the internuclear distance between them and they get closer and closer together, you notice here, guys, that the potential energy is decreasing and finally will reach a minimum. Here's why that happens. Okay, let's look over here. Here we have our separate hydrogen atoms. Okay, here's my nucleus, and here in the diagram, these dots here are representing my electron cloud. Now remember that hydrogen has only got one valence electron, okay, but what these dots are showing is the regions where it's probable to find that electron, okay? It's most probable to find it near the nucleus and then less probable as you go farther out. When these atoms come closer together, okay, this is hydrogen A, we'll say, over here, and here's hydrogen B. Okay, this hydrogen nucleus is attracted to its electron, which is somewhere here in the vicinity. But you can imagine, as these guys get closer, their electron clouds start to overlap. Okay, if this right here is like, say, the electron from hydrogen atom B, and this one here is the electron from hydrogen atom A. Okay, there's gonna be some time where these electrons are kind of like between the two nuclei. You can imagine this nucleus is attracted to its electron, but it's also attracted to the electron from hydrogen atom B over here. In the same way, the nucleus from hydrogen atom B is going to be attracted to its electron, but also to the electron coming from hydrogen atom A over here. Okay? So as the atoms get closer together, the nuclei become attracted to each other's electrons. And so you can see as this distance here decreases, the potential energy is going down. It becomes negative because the atoms start to become attracted to each other. Okay? Now finally, okay, you're going to reach a minimum point right here. And what that minimum represents is the point where that attraction is at a maximum, okay? And what you got here, okay, is, we have these, the electron density here, so we have this area in the middle where the electrons are going to spend some time, okay? They're kind of, in that region of space. When that happens, they're attracted to, both the nuclei are attracted to these shared electrons here in the middle, and that's what leads to your bond. That's why we say they share electrons, because when their electron clouds overlap, there's a high probability of finding the electrons here between the two nuclei. When that happens, the nuclei are attracted to the electrons in between them, and that mutual attraction for the electrons is what causes, or what is, the covalent bond, is that attraction to the electrons from both nuclei. Okay? So that's kind of like the optimum point. Now this distance where that attraction is at the maximum, that is called the bond length right there. That's the distance between the nuclei where the attraction is greatest. Now you can imagine, guys, if we continued, I'll just switch colors here a little bit, okay? No, there we go. Okay, now you can imagine, guys, that even these nuclei are attracted to the electrons here, but they also repel each other. Okay, now when they're far apart, that doesn't really happen to that great an extent. But imagine, guys, if I continued to decrease the distance between the nuclei, and eventually those nuclei got closer and closer together, they would repel each other too. So there comes a point, if I squish the nuclei close together, it turns out that repulsion becomes strong in the attraction, and as I put them closer and closer together, they'll repel more and more and more and more and more, and so the potential energy goes to infinity as that repulsion kind of overcomes the attraction to the electrons. That's what this graph here is showing, okay? But keep in mind, guys, the covalent bond, okay, what that results from, is the attraction of these nuclei, okay, to the electrons that are in between them. That's what a covalent bond is. Now, a lot of times we'll represent a hydrogen molecule like this. I'll draw an H and then a dash and then an H, where that dash there represents electrons that are shared in between the two nuclei. Remember that this is just a model to help us understand what's going on. It is not really accurate physically to draw a dash here and say, okay, well, the electrons are stuck in between these two hydrogen nuclei, because really they're not, right? This is actually more accurate picture where we show, well, the electrons really spend some time out here and whatever, but it's most likely to find them in between the nuclei, and the attraction of the nuclei to those electrons is what makes the bond, okay? So just kind of keep in mind really what's actually going on. Okay, let me go back to blue here. Let's go on. Okay, now it turns out, guys, that we're going to represent molecules, okay, that engage in covalent bonding using something called Lewis dot diagrams. And I'm going to show you guys how to draw Lewis dot diagrams. I'm going to give you guys some rules that are a little bit different probably from what it is that you learned last year, but that's okay. You'll see why we do it differently later on, okay? Now, Lewis dot diagrams are named after a very famous chemist named Gilbert Newton Lewis, okay, and that's a picture of him down here. Now, it turns out, guys, that Gilbert Newton Lewis was really famous for a variety of things. Later on in the year, we're going to talk about his contributions to acid-base theory. If you've ever heard of Lewis acids, okay, that's this guy right here. Yeah, he also discovered, or rather, I guess you could say, gave us the idea, some other, ideas about how to understand acids and bases, and so that's, called Lewis acid-base theory now in his honor. He also did a lot of work with heavy water, which is, D2O, where the D stands for deuterium. He did a lot of different things. Yeah. So Lewis structures are named, or Lewis dot diagrams, these pictures we're going to draw are named in his honor because he's the first person really to propose something called the octet rule, okay? when we draw these structures, what we're going to do is we're going to represent valence electrons using dots. And the principle here that guides the drawing of these structures is that each element wants to have a noble gas electron configuration, and this rule is called the octet rule. Okay, we kind of say that most elements want to have 8 valence electrons that they can count as their own. Okay, and this can be achieved through covalent bonding when elements share electrons. This is kind of like the rule that governs how they're going to do that. Now, there are some exceptions, okay? The exception here to the octet rule that you're going to have to remember most of the time is hydrogen. Hydrogen only wants 2 valence electrons. That's all it can ever have. And something you need to remember all the time. It can only ever have 2 valence electrons, meaning it's only going to ever form 1 bond, okay? Let's look at an example. The formation of the compound hydrogen fluoride. If you look at the element hydrogen, hydrogen has got 1 valence electron, which I'm going to draw here as a dot. This would be a Lewis dot diagram for the element hydrogen. Fluorine we can represent like this, okay? Fluorine, if you look on the periodic tables in group 7, it's going to have 7 valence electrons, and we can represent those as dots we draw around the atom right here, okay? Now, what these guys both really want to have is they both want to have a full outer shell. For hydrogen, that's going to be 2 valence electrons. For fluorine, that's going to be 8 valence electrons. Individually, they don't have that, but they can get a full outer shell by sharing electrons, okay? Here's how they can do that. Hydrogen will share its electron here with fluorine, and fluorine will share this electron right here with the hydrogen. When it shares these electrons, okay, that will form a covalent bond. So these electrons are going to be located primarily between the 2 nuclei. There will be mutual attraction from the fluorine nucleus to these electrons, from the hydrogen nucleus to these electrons, okay? And so now it forms the molecule hydrogen fluoride. Now when we draw the Lewis dot diagram for the compound, we're going to draw the shared electrons in between the 2 atoms like that, okay? Now what this means is that these electrons here are shared between both atoms. Both atoms now get to count these electrons towards their total. So hydrogen gets to count both of these. Hydrogen now has 2. Fluorine gets to count both these electrons in addition to its other 6. And so now it has 8 valence electrons, and they're both happy. Now you guys are going to more commonly, this is one way I could draw it, you're going to more commonly see me draw it like this, where I use a dash to represent a pair of shared electrons, and then dots to represent electrons that are not used to form bonds, okay? This is another way I can represent the hydrogen fluoride molecule, okay? And that would be its Lewis dot diagram. And there we go. Now, what we're going to look at here for the rest of the podcast is how to draw a Lewis dot structure for more complicated molecules, okay? And there's a few rules we need to go over here first. Here they are, okay? When we're drawing a Lewis dot structure, the first thing we're going to do all the time is we're going to select what the central atom is going to be. And this is, for simple molecules. We're going to select the central atom. And the way you do that is you find the one that has the lowest electron affinity, okay? For example, consider the molecule carbon dioxide, okay? Now, you guys have seen this molecule enough times. You know that carbon is going to be the central atom. But say you didn't know that carbon is going to be the central atom. The way you can figure that out is because compared to oxygen, carbon has a much lower electron affinity. That's usually going to be the way that it is. Okay, the second step is we're going to take this molecule and we're going to look at all the atoms that are in it, and we're going to add up all the valence electrons that each of those bring to the party. The third thing we're going to do is we're going to use 1 pair of electrons from each atom, or from the total rather, to form a bond between each bonded pair of atoms. Next, we're going to put the remaining electrons around to satisfy the octet rule, so that each atom that's bonding has 8 valence electrons that it gets to count. The exception, of course, for this is going to be hydrogen. If I ask you guys how many valence electrons can hydrogen have, you're going to tell me, of course, Mr. Harper, it can only ever have 2, which means hydrogen will only ever form 1 bond. Ever. Make sure you remember that. It only will form 1 bond. Okay, let's take a look at some examples. We're going to draw Lewis structures for these molecules right here. H2CO, which is called formaldehyde, nitrogen trifluoride, carbon dioxide, and this guy right here, which is called phosgene, which incidentally is a chemical weapon. Let's take a look first at nitrogen trifluoride because it is the easiest example, okay? I write down here the formula, NF3. If I look here what the central atom is going to be, it's going to be my nitrogen, okay? Let's count up the number of valence electrons it should have. Nitrogen's a group 5, so it has 5 valence electrons. Fluorine has got 7. Each one's got 7. We have 3 fluorines, so 3 times 7 is 21. Plus 5 is we're going to have a total of 26 valence electrons to use. Okay? Now I'm going to start drawing my Lewis structure. The nitrogen's going to be my central atom. It's going to be surrounded by 3 fluorines. Since I know the central atom here is going to be bonded to each of the fluorines, I'm going to use one pair of electrons to make a bond between the nitrogen and each of the central atoms. Okay? In doing so and making these 3 bonds, keep in mind that each of these lines represents 2 shared electrons. Okay? I've just placed 6 valence electrons. I'm going to just kind of keep track over here. Okay? I've used 6. I've got 20 electrons remaining to place. Okay? So let's start doing that in order to fulfill everything's octet. Fluorine here, each one's already got 2 valence electrons. Each one needs 6 more to be happy. So I'm going to put 6 dots around each fluorine to represent valence electrons I'm placing. Okay, now I've just used 18 valence electrons. I'll subtract that from my total. Okay, I've got 2 electrons remaining left to place. If we look here now at the central atom is not happy yet. Okay, it's got 6 valence electrons. It wants 2 more. I've got 2 electrons left. I'm going to put that as a lone pair here on my nitrogen. Now I use those 2. I've got 0 left. Everybody's happy. And so this is a good Lewis structure. Ta-da! It's great. And there we go. Excuse me. Okay, let's look at the next one, guys. The next one we're going to do here is carbon dioxide. Okay? CO2. If we look at carbon dioxide, it's got 2 oxygens. Each oxygen has got 6 valence electrons. The carbon has got 4. So it's got a total of 16 valence electrons that we're going to use to draw the Lewis structure. The central atom here is going to be carbon, like we said before, so we're going to draw a carbon. Okay, and it's surrounded by 2 oxygens. The next thing I'm going to do is I'm going to draw a bond between the central atom and each of those oxygens right there. Okay, I just drew two bonds down. I used 4 electrons, so we got 12 electrons left. Okay, now let's try to fulfill the octets of the perimeter atoms. I'll put my 6 electrons here to fulfill its octet. I'll put 6 electrons here to fulfill its octet. And there we go. Now we've used 12 electrons. Okay, we have none left. All right. And now if we take a look next at the central atom is not happy. So darn it, guys. This Lewis structure does not work. Okay. Now notice what I did here in my approach. I put the bonds first. Then I tried to fulfill the octets of the peripheral atoms here, not the central atom. If this doesn't work, where I can't just put lone electrons, the next thing I want to try is, instead of having all these electrons here on the peripheral atoms, I'm going to move this pair here to form a double bond. Okay? If I do that, this side's going to look like this. I've got my oxygen here with 2 sets of lone electrons and a double bond to my carbon. Okay? I'm going to try the same thing over here now, because I want to fulfill the octet. I'll move this pair of electrons on here. We'll make a double bond. Okay, so there we go. This has now got a double bond between the carbon and the oxygen. And it's got 2 lone pairs of electrons on the oxygen right there. This is a good Lewis structure. Now my carbon atom here has got 8 valence electrons it gets to count. Each of the oxygens has 8 valence electrons it gets to count, because each atom gets to count at the double bonds. Okay, so this is 4 electrons, 6, 8. 4 electrons here is 8 for the carbon. 4 electrons here plus 2 plus 2 more here is 8 for this oxygen. Everything's got a full outer shell, and so there we go. As a rule of thumb, guys, do not make double bonds unless you have to fulfill the octet for something. Start with single bonds first, and then if you have to, make multiple bonds. Okay, let's do one more here. Let's do this guy right here, which is going to be formaldehyde. Okay? The formula is H2CO. If I total it up, I have 6 valence electrons on the oxygen, 4 on the carbon, 2 on the hydrogen. So we have a total of 12 valence electrons to place in our structure. Again, the central atom is going to be my carbon. So we got a carbon, and an oxygen, and a hydrogen, and a hydrogen. I'm going to place a bond here between the central atom and each of my peripheral atoms. So we're going to have a bond, and a bond, and a bond. Okay, like that. When I did that, I just used 6 electrons. I've got 6 electrons left. Next, I'm going to try to fulfill the octet for each of my peripheral atoms. So we're going to go dot, 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 dot. Okay? If I take a look now, oxygen's got a full octet. The hydrogens each have 1 bond. They've each got 2 valence electrons they can count, so they're both happy. But my carbon, regrettably, is not. Since the carbon is not fulfilled, I'm going to move a pair of electrons here to make a double bond. If I do that, now my structure is going to become carbon with a double bond to my oxygen, like this. And then my two hydrogens, like that. Okay? And there we go. Now, this is a good Lewis structure for formaldehyde because I look at my carbon. It's got 1, 2, 3, 4 bonds. Each bond has two electrons, so it gets to count 8 valence electrons total. The oxygen here gets to count 2, 4, 6, 8 electrons, so it is happy, and the hydrogens are happy, and everything's good. So here's my good Lewis structure. Okay, guys. Here's what I want you guys to do. Pause the podcast, and I want you guys to try to draw the Lewis structure for Cl2CO. This is phosgene, a chemical weapon. Do that, and I will come back and then restart it after you guys have done that, and I will go through the solution with you. So pause. Okay, guys, now we're back. If we take a look here at this molecule, which is phosgene, okay, the central atom is going to again be carbon because it has the lowest electron affinity. Notice a pattern here, guys. Carbon is the central atom a lot of the time. If we look at how many valence electrons we have to place, the oxygen comes with 6, the carbon brings 4, each chlorine brings 7. If we add that all together, we have 24 valence electrons total that all the elements here have brought to the party that we need to distribute. Now let's set it up. The central atom is going to be carbon, and we're going to have our oxygen and a chlorine like that, okay? Next step is I'm going to draw a bond between the central atoms and each of the peripheral atoms. So we're going to go bond, bond, and bond. When we do that, we have just used 6 electrons, so now we have 18 left to place. I'm going to start by trying to do that without making any double bonds, and so I'll put those around my peripheral atoms. We go dot, 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 dot. That one's got 6 more now for a total of 8. I'll put 6 around this guy here, dot, 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 and then 1, 2, 3, 4, 5, 6, like that, okay? If I look at it now, I've just used all the rest of my 18 electrons. Those are all gone. Okay, so I got none left, which is good. But the carbon now does not have a full outer shell of electrons. Okay, so now that tells us because I can't make a full octet for everything, now I have to make a double bond. I'll move a pair of electrons and make it shared. Now it turns out that when I do that, okay, this is going to be the one that moves right here. And so the Lewis structure we're going to get, if that happens, is we're going to get carbon with a double bond here to my oxygen, and then a single bond to each of my chlorines, like that. Now, you might ask, well, Mr. Harper, why is it that that happens? Because couldn't you just as easily say, well, instead of the oxygen forming a double bond to the carbon, why doesn't the chlorine do that? Because I could move this pair of electrons there, and then if I did that, I'd make a Lewis structure that looks like this. We'd have chlorine with a single bond to oxygen, like this, and with a chlorine like that, and then a double bond here to this chlorine, like that. Now, this is also true, guys. If I look here at this Lewis structure, this would also fulfill the octet rule for all the elements that are bonding. But there's a reason why this one right here is the correct Lewis structure, and we're going to get into that in the next couple days. It's an argument called formal charge. We use a guideline called formal charge to determine what the best Lewis structure is. There's more than one possibility. We'll go over that later, just except for right now, though, that this is the good one, and this guy right here is not the best one. So this is the one we want right here. But if you'd written this one down here on your paper, like for homework, before knowing about formal charge, I wouldn't mark you wrong. But we'll learn why in the next coming days, why this isn't the best one, but this one is. Okay. One more thing we're going to talk about today, guys. Okay, the last thing we're going to talk about today, guys, is something called resonance structures. It turns out that once in a while you can draw for the same molecule 2 equivalent Lewis structures. And what I mean by equivalent is that the atoms are connected the same way, but all that is different about them is the placement of the electrons in the molecule and the way the bonds are formed, okay? Not how the peripheral atoms are connected to the central atom and nothing else. It's only about the placement of the electrons that's different. Let me show you guys an example. We're going to, there has this on your paper. We're going to skip ozone for right now. Let's just look here at the carbonate ion. If you look at the carbonate ion, okay, and we think about how many valence electrons it's got 4 from the carbon and 6 from each oxygen. 6 times 3 is 18, plus 4 is 22. Now, this is a 2- ion, meaning he's got 2 extra. So we've got a total of 24 valence electrons to place. If I do that, if I draw a Lewis structure here for my carbonate, carbon central atom, I'm going to have a bond to an oxygen, bond to an oxygen, bond to an oxygen. And it turns out, guys, we have to have one double bond in here to fulfill everything's valence. So I'll draw this Lewis structure for you guys right here. Okay, dot, 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 and then dot, 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 like that. Now, when we're drawing the Lewis structure for an ion, guys, it's customary to put that turkey in brackets like this. Okay, and then on the outside to show the charge. That's a 2- charge. Okay, now here we have a carbon connected to each of these 3 oxygens. what if I drew it like this instead? Okay. Here we have a bond to an oxygen. Here's another oxygen. And here's an oxygen right there. Okay. This also would be a valid Lewis structure here for my carbonate ion. Okay. This has also got a 2- charge. Okay. The only difference between these two structures that I just drew is the location of that double bond. Here I have between the carbon and this oxygen. Here I have between the carbon and this oxygen right here. Now notice I could also draw a third structure like this, where I've got a single bond there and a single bond there and a double bond to this other oxygen over here, okay? These structures, guys, are equivalent. They have the same connectivity of the atoms, but a different placement of the double bond. These are resonance structures, okay? That's what these are. They, equivalent structures for this thing, which only differ in the way that the electrons are placed, not how the atoms are connected. Now, it turns out, guys, that if you looked at each of these resonance structures, you would expect, actually, that the carbonate ion should have 2 different kinds of bonds between the carbon and the oxygen. You would expect that you would see experimentally single bonds and also double bonds, okay? It turns out that is not actually the case. Why this idea is important, by the way, guys, is because, if any of these structures actually was the correct structure, okay, it turns out the single bonds and double bonds behave differently. Double bonds are shorter and they're also harder to break. So you would expect to see 1 short bond and 2 long bonds if we used spectroscopy or some other method to examine a carbonate ion. But in fact, that isn't what you actually see. What you really see, if we examine a carbonate ion by experiment, is there's only 1 type of bond, okay? And it's kind of like an average of all 3 of these structures, okay? So we're going to have what the real experimental case is this. We've got a carbon and an oxygen, a carbon and an oxygen, a carbon and an oxygen here, and then each of these bonds is kind of like a 1 1/3 bond. This double bond is actually distributed. It's kind of like an average of each of these structures. This double bond is distributed amongst each of these the single bonds. We're gonna look at why that is, a really good explanation, okay? But this thing that I drew right here, this is called a resonance hybrid, okay? And this is kind of like, if you can imagine that you take the average of each of these 3 structures, you add these 3 structures together and divide by 3, you get the average, and that's the resonant hybrid, okay? Where each of these bonds is the same, and it's like a 1 1/3 bond, okay? Anyway. So, because it turns out that if you do look at the carbonate ion, you really only have 1 type of carbon-oxygen bond. They all, incidentally, are the same, okay? So we're going to talk a little bit more about that tomorrow, guys. That's the end of the podcast for tonight. Please make sure that you bring your notes with you tomorrow. Be ready to rock and roll in class, and I will see you then. Have a nice night. Goodbye.